So this time, you can be sure that tau is very close to 0. Okay? In the surface between fluid and air, between liquid and air, the shear stress is very small. It is close to 0. So what happens is, if tau is equal to 0, you know tau is mu du dy. So du over dy is equal to 0. That is where you got that. At y equal to d, du over dy is equal to 0. Okay, now I change again the thickness from h to b. Now I change to d, so that to make you a bit confused. Just to give you an idea that that one is nothing but a symbol. I can change it. Doesn't really matter. You do not need to worship h. It's just a symbol. You can change it, right? You can change it to a, b, c. Even if you like p, you can put p or k or l or m. Doesn't really matter. Just a thickness. You will change it with number at the end of the day, right? Okay, so that's the two changes that I make. One is the direction of the coordinate. Second is the free surface, right? Rather than having a wall, you are now having a free surface. So how do we analyze it? Okay, it is the same. You need to look at the condition. Now the condition is the layer of the fluid has a free surface. That is your boundary condition. The shear stress at the surface between air is small and negligible. That's why you get that du dy equal to 0, right? And then the depth is given, and then the viscosity is given, flowing down. Okay, you know the angle is theta. One very important thing, the pressure does not change in the streamline direction. What does it mean? dp dx will be equal to 0. Okay, but that is only applicable for this case. You will realize in your tutorial that I can do a bit more than that. Just giving you dp dx equal to something, then you can cancel it. Okay, but this case, because I want to give you an example, of course I want to make it a very simple. Okay, so I put dp dx equal to 0. So what will happen is, because your dp dx is equal to 0, you realize last time your dp dx is not scratched, now it is scratched. This one scratched. But, see this? Previously, we don't have gravity in the x direction. But, since we choose our x direction to be this, of course, your gravity, you cannot just force them to follow the y. Right? You cannot make the gravity to walk this way. No way. Gravity is very stubborn. Doesn't matter what, we'll just go there. Right? You like it or not, this is the way. Okay? Just like your lecture. Like it or not, this is the way. There is no other way. Okay, so this is your plate. This is your theta. This is your x. This is your y. When you look at it, this is your y, right? This is your negative y. And your gravity is working to this direction. Right? So if you look at this, you take the parallel, it will be like that. Here. So this is your g. If you look at it, this one will be your gx and this one will be your gy. Since your theta there, you got your 90 degree there and 90 degree there. Right? You know that if this is the case, I make myself efficient. Just put alpha. The alpha here will be similar to the alpha there. And this one will be your theta. Which means your gx is g sine theta in front. Right? And then your gy is negative g cos theta. Why it is negative? Because gravity is working in the opposite of the y direction. It is on this direction. So that's why you get negative g cos theta. Clear? Until this point, am I going too fast? Okay. If not going too fast, now I need to speed up a little bit. You get your rho gx there, you get dp dy, dp dz, because only dp dx is 0. The other two, we do not know whether it is 0 or not, we have no information, so let it be like that. Let them happily like that. Don't disturb them. Okay, now if you look at it, you get 0 equal to mu d square u dy square plus rho gx. If you compare with the previously derived equation, when you have horizontal, you get this, right? When you have this, now you realize that we have mu du over dy square equal to minus rho gx. Why so difficult? Okay, so when you change it, you will get d square u over dy square equal to 1 over mu rho gx. That thing. Okay. This is this condition now. If you realize in your in your tutorial number 2, what happens if your dp dx is not 0? When your dp dx is not 0, basically you will have 0 is equal to minus dp dx, because dp dx is not 0, plus mu d square u over dy square plus rho gx. This one minus, right? So you will end up having mu d square u over dy equal to dp dx minus rho gx. So you can see the only difference is you have another dp dx. See? This one when you have only dp dx, this one when you have only gravity, this one when you have both. Clear now? That's why I told you. The first one is the most crucial one. Once you overcome that problem, the rest is just a piece of cake. Okay? So you can see dp dx, rho gx, dp dx and rho gx. This one again. Clear, ladies and gentlemen? Okay. Oh, suddenly I spent 1 hour. Okay. So what next? We are taking this one again. Okay, we are not talking that. That one is your problem. This one is my problem now. Okay, I have this. So I double integrate it. Since g sine theta is not a function of y, so you can just double integrate it towards y. So you can imagine you will get y squared plus c1 y plus c2. Right? So that's what you will have. And now, you see this one, previously you have 1 over 2 mu dp dx. Now you just change into this. So if you have dp dx and g, you will have 1 over mu dp dx minus rho g sine theta. As simple as that. Right. Don't worry too much about it. You have a lot of other things to worry, not fluid mechanics. Okay? So now, this boundary condition surely will give you C2 equal to 0. Right? You know why? Because y is equal to 0 at, u equal to 0 at y equal to 0. So you have C2 equal to 0. Now the problem is this, you never found it before. Right? Usually you will have u is equal to 0 when y equal to h. Now in this case, not u, but you need to derive it one time. So it is du dy that is 0, not u. So what you need to do is, you take the derivation of it. This is your C2 equal to 0, so you don't have any C2 there. Even if you have C2, when you derive it, C2 will be gone. So it doesn't really matter. So you derive it, when you derive, it becomes this, right? Nicely, because you just need C1. You don't have any y anymore. No h, no nothing. So whatever it is your C1. As simple as that. So you plug in back, you will have your, okay, as I said to you before, forget about these two. Forget about these two, just remember the first one. Because the first one is the generic equation plus C1. Right? C1, you have to replace it with some value. Dear ladies and gentlemen, are you happy now? Okay, if you are happy with that, please try to solve this problem example, and see what happens if the angle of this become 90 degrees.